Hey guys, welcome back. Awesome. So, we're going to continue our discussion on entropy now. So, let's see what we're going to be talking about today. Maybe. Okay. So, on our agenda, the three laws of thermodynamics, spontaneous process, what that means. We're going to define entropy, and then we're going to talk about its relationship to the second law of thermodynamics. Okay. So, that's where we're going. All right. Questions, comments, problems, concerns. Hopefully not, but email, WebEx, phone, you name it. Get a hold of me. We'll talk. Thanks. So the laws of thermodynamics. Now, the first law of thermodynamics we've already talked about. It says that energy cannot be created or destroyed. Okay, got that one. Awesome. Second law of thermodynamics says for a spontaneous process, entropy of the universe increases. And the third law of thermodynamics says a perfect crystal at 0 Kelvin has 0 entropy. Well, okay, great. I've seen entropy twice in these discussions. What the hell is entropy? Well, we'll define that shortly. We also see the term spontaneous process. Spontaneous process is defined as a process that happens without any intervention, that will not undo itself in nature without intervention. So the reaction is spontaneous in one direction, but not in the other direction. So it always wants to go one way, but not the other way. And there are a lot of factors that are involved that help us determine which makes it spontaneous. Now, what determines if a reaction is spontaneous? Well, there are a number of things that we have to be able to look at. So the change in heat is one, those enthalpy changes that we've already talked about. Generally speaking, exothermic reactions, those that give off heat, are more spontaneous than endothermic ones. But not all exothermic reactions are spontaneous. So that's not enough. That's what I learned from that, is that that's not enough. So there has to be something else involved in this. Well, another thing that's a factor in this is the change in order. That's an entropy change. Entropy is a measure of how spread out or dispersed the energy of a system is among the different possible ways that system can contain energy. So the greater the dispersal, the greater the entropy. So that's related to things like how many different positions can this particular molecule take? And in a solid, it has fewer options than it does in a liquid. How many bonds does this particular thing have? Where are the electrons distributed in this particular molecule? There are a lot of different things that we talk about there. Entropy is a way of measuring the disorder of a system, how random that system is. The more random it is, the more favorable it is. And that is a better entropy state. So we want random. Random is good. Okay, so that's what we're talking about in terms of entropy. It's a randomness of the system. Okay. Now, again, entropy. It is possible to measure absolute entropy. Okay, standard entropy is the absolute entropy of a substance of 1 atmosphere, and usually quoted with its value at 25 degrees C for 1 mole of substance. It can be either listed as joules per Kelvin or joules per Kelvin mole. The value is for 1 mole of a substance. So it doesn't matter which units we have, it's always for 1 mole of that substance. Entropies of elements and compounds are all positive. All of these values will be positive because everything has more entropy in it than an absolute entropy would have. So a perfect crystal at 0 degrees Kelvin has no entropy. That was that third law. So everything else has more randomness than that. So more complex molecules have higher entropy values. There are more places that the energy can reside in the number of bonds that it has and the number of positions of the electrons. Gases are less ordered than liquids, so that means that entropy values are higher in gases compared to liquids. Heavier atoms have a higher entropy because there are more ways to organize the nuclei and electrons in larger atoms. Okay, so there are a lot of factors that go into this, but it really has everything to do with how many different ways can I arrange that energy that exists. And that energy exists not only in bonds, but also in the position of the nuclei and the electrons, and in how much freedom that particular molecule has based on its state. Okay, so those are things that we can talk about in terms of entropy. So the second law of thermodynamics says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So in equilibrium, the entropy does not change. We go forward, we go backward. So it doesn't matter what we're doing, net change is not noticeable. It's not measurable, which is the same way that we defined the change in the equilibrium constant, is that we don't notice any changes in those values in terms of concentration. So that's how we know we're at equilibrium. Okay. For a spontaneous process, the delta S of the universe, so entropy is listed as delta S, and the delta S of the universe equal to the delta S of the system plus the delta S of the surroundings is greater than 0. For an equilibrium process, the delta S of the universe is equal to the delta S of the system plus the surroundings, and that's greater than 0. Okay. It's actually equal to 0. I'm sorry, that should say equal. So if the delta S of the system is negative, the process is not spontaneous in the direction described. It's spontaneous in the opposite direction. Okay. Entropy changes in a system can be calculated in the same way that we calculate our enthalpies. Okay, so we look at those tabulated values and we find the sum of the products times their stoichiometric coefficients minus the sum of the reactants times their stoichiometric coefficients, and that'll give us our absolute entropy. Okay. Standard entropy values are given in the exam handouts. So these used to be in the exam handouts on page 10, table 17.1. And I apologize because they're no longer there. You will have to be given these values on a test to be able to work with these. I haven't made them pretty, so they don't exist in this one yet. So if the value you require for a calculation is not in that table, you should be given that value on a test. Now remember, that value may not exist exactly where you are. You may have to look somewhere else on that test. So the handouts that are given with the test have some values on it. So the ones that were just recently made available in the content, but it may actually be in another question that's on that test. So that value may be present somewhere else. Okay. Again, I'm so sorry. If a reaction produces more molecules of gas than it consumes, delta S is greater than 0. If the total number of gas molecules goes down, delta S is less than 0. So more gas molecules is good. More molecules of gas in the end is good. If there is no net change in the number of gas molecules, then delta S could be either positive or negative, but will be very small. So our biggest factor is in going from like liquid to gas or solid to gas. That phase change is our biggest factor, but it is not the only consideration. Okay, so that's our second law of thermodynamics. Okay, so there is a relationship between the reaction enthalpy and the entropy of the surroundings. So if the enthalpy of a reaction is negative, if it's exothermic, if heat is given off to the surroundings, then the disorder in the surroundings goes up. So the entropy goes up in the surroundings. Okay, so it's therefore positive. If the enthalpy of the reaction is positive, endothermic, heat is taken away from the surroundings, then the disorder in the surrounding goes down. The entropy goes down and is therefore negative. So the delta S of the surroundings is the same in size but opposite in sign to the delta H of the system over temperature. Entropy of a perfect crystalline substance is 0 at the absolute 0 of temperature. Doesn't happen, but that's what it would be. Entropy above absolute 0 is always positive because there is some molecular motion. It is also positive at absolute 0 for a material that is impure, since there's disorder in that solid. So it would have to be completely pure for it to have a value of 0. That is not likely. Okay. This image that you're looking at here is that in the solid phase, remember, as we add temperature to this, that temperature goes up, these things begin to move and move and move and move and move, and then they melt. Okay, so my temperature doesn't change, but my entropy I'm still adding entropy to this by making it able to move. Then our temperature goes up again in the liquid phase, and then we go to the boiling. So we break those bonds, leave the liquid phase to get into the gas phase. And so my entropy has gone up significantly when I do that. I notice that it's a bigger difference between liquid and gas than it is between liquid and solid. Okay. And that change with energy with temperature goes up slightly as we get to liquid and more as we get to gas. Okay. So there's more of an effect for the same amount of temperature that we put in. Okay. Cool, that's fun. So questions, comments, problems so far? No, I hope not. So there's a lot of theory, things that we're going to be talking about. We'll see how this applies a little bit later on. I'm going to go take a break and do a stop here, and I'll be back with you in just a minute.